In this video, we will learn how to calculate the center of gravity and center of mass for simple and composite volumes, as well as the centroid for simple and composite volumes. In order to determine the location of a center of mass of a volume, let's consider that the center of mass is at some unknown location for now, y bar, x bar, and z bar from the origin. Let's also consider a differential force called dW located at x, y, and z. In this derivation, we will assume that gravity is in the negative z hat direction. In this example, we have the weight of the entire volume acting at the center of mass, g, of our volume. Let us consider the moment that this would cause about the origin. In order to do this, we could draw a position vector r, O to g, from the origin to g, the location of our center of mass. So ROG will be x bar I hat plus y bar j hat plus z bar k hat. The moment that this weight would cause about the origin would then be simply using our definition of the moment, r, O to g, crossed with the weight. Plugging in ROG and what we know for the weight, since we said that weight is acting in the negative k hat direction for this example, we have that this is equal to x bar I hat plus y bar j hat plus z bar k hat crossed with minus w, the magnitude of the weight of the entire volume, in the negative k hat direction. Carrying this cross product out, we find that this is equal to x bar w j hat minus y bar w I hat. Next, let's consider that the moment that our differential weight causes about the origin. Let's say that our differential weight is acting at a point chi. So we can draw a position vector from the origin to chi, that is RO to chi. So the moment from our differential weight about the origin is simply RO to chi crossed with our dW. Using the same analysis as before, we can see that this is x dW j hat minus y dW I hat. Now that we have the moment caused by a differential weight about the origin, we can reconsider how we think about the moment caused from the entire weight of the volume about the origin. We can think of it as the sum of the moment of the differential weights about the origin over the entire volume, or integrated over the entire volume, which is simply the integral of the entire volume of x dW j hat minus the integral over the entire volume of y dW I hat. We can set this equal to our moment we found earlier of the entire weight acting at the center of mass. So it is equal to what we found as x bar w j hat minus y bar w I hat. If we dot this entire equation with I hat, we can convert this vector valued equation into a scalar value equation, that is the integral over the entire volume of y dW. So I am taking this part because j dotted with I is simply 0 and I dot I is 1. So that's how I get the integral of the volume y dW is equal to y bar w. Since we wanted to solve for the position of our center of mass y bar, we can set this equal to the integral over the entire volume of y dW divided by the entire weight. Similarly, we can dot our moment equation of the weight about the origin with j hat. That will give us that the x bar location is the integral over the entire volume of x dW divided by the weight. Now that we've solved for y bar and x bar in terms of our differential weight and the weight, recall that our weight is equal to mass times gravity. Therefore, our differential weight is our gravity times a differential mass. We know that our mass is equal to the integral of our density over the entire volume. and that the differential mass is simply the density times the differential volume. We can substitute in our weight and differential weight into our equations for y bar and x bar. This gives us that the integral over the volume of y times gravity times the differential mass over mg is equal to y bar. Also, x bar is equal to the integral over the entire volume of x times gravity dm divided by mg. Next, we can sub in for dm and m. So we get that y bar is equal to gravity times the integral over the entire volume of y times the density dv over g times the integral of the density dv. We can cancel out gravity and pull that out since it is a constant, and we get that y bar, so the location of our center of mass from the x-axis here, it's y bar, is equal to the integral over the entire volume of y times the density dv over the integral of the density times dv. Similarly, x bar is equal to the integral over the entire volume of x times our density dv divided by the integral of the entire volume of our density dv. We can derive z bar, so the location of the center of mass in the z direction, using the same method we used for y bar and x bar by simply rotating the mass so that the gravitational force acts in either the x hat or I hat direction and the j hat direction. That would give us that z bar is equal to the integral of z times the density dv over the integral of the entire volume of the density dv. In your textbook in 6.14, y bar is referred to as ym, which is the location of the center of mass in the y direction. X bar is referred to as xm, and z bar is referred to as zm. Another useful topic is to determine the centroids, or the position of the centroid of a volume, area, and a line. For a centroid, we will assume that our material is homogeneous, therefore it has a uniform density. Let's go back to the equation for x bar, or the x position of the center of mass. Recall that that was equal to the integral over the entire volume of x times the density dv over the integral over the entire volume of the density dv. If density is constant, we can pull it out of the integral and cancel it out. Therefore, that the x of the centroid, so the x position of our centroid, is just the integral of x dv divided by the volume. Similarly, the y position for the centroid is just the integral over the entire volume of y dv divided by the volume, and z centroid is the integral over the entire volume of z dv divided by the volume. Using the same method for our area, if this is a planar problem, we have that the centroid is just the integral over the area of x dA divided by the area, y is equal to the integral over the area of y dA divided by the area, and zc is equal to the integral over the area of z dA divided by the area. If we want to know the centroid for a line, we integrate over the line x dl, that's divided by the length. The y centroid position is the integral over that line in the y dl divided by length, and the z position of the centroid of our line is over the integral over the line of z dl divided by the length. So this is our formulas for centroids of volumes, areas, and lines. Since it is common to want to know the centroid for shapes, in your appendix you'll find there are the centroids for common areas such as a rectangle, triangles, circles, quarter circles, and there's also the centroids for cylinders, cubes, half cylinders or semi-cylinders, cylindrical shells, spheres. So you can find the already calculated centroid for common shapes in your appendix. That's Appendix C in our textbook. What happens if we get an irregular shape, such as this shape in this diagram, figure A, from your text, SAB, in section 6.6? Taking the integral of this irregular shape will be quite painful. However, we can think of it as a composite of several shapes that we already have the centroids for. We have a rectangle, a quarter cylinder, and then a negative shape of a cylinder and another negative shape of a cylinder. Individually, we know the centroids of all of these shapes. So we can say that the centroid, or the center of mass, of the entire shapes is just simply the sum of the mass of each component times its x centroid location divided by the total mass. This holds true for the y position of the center of mass and the z position of the center of mass. So instead of integrating a complicated shape, we will just take the sum of each component's center of mass normalized by its own mass